Hello and welcome to the webinar on IQS Proximity Systems. It will be hosted by me, Ricardo Madureira,
and Gaël Coron from Technical Center of Excellence in Fribourg, Switzerland. In this webinar, we will explore the additional features now available with live example. We will also address the topic on wiring best practice and common issues in the field. We will also present to you a new member of the TQ IQS family, and we are sure that you will appreciate it. It's the IQS 910. So stay tuned. A proximity probe, well, it does what its name implies. It measures a distance, so it will give you the distance between the tip of the sensor and the target. It can do it with an amazing resolution. In fact, I was in discussion with the product line manager of the sensor and conditioners, and he told me that in some special application they can discriminate distance in the order of few nanometers. Now, it's not surprising, because in normal day-to-day application, her sensors can discriminate distance smaller than few micrometers. Proximity probes are one of the most present sensors in protection and condition monitoring. The reason is simple. If you think about protection and condition monitoring of a machine, physical distance and movement are the things that come quickly to your mind. They can be used in many different types of measurements. You can also combine the information of two probes or combine them with other types of sensors to measure, for example, the absolute vibration of a shaft. Note as well that, of course, speed can also be measured with a proximity probe. In fact, TQ proximity probes are the preferred ones, given their simplicity and high reliability. They are present in many different places of the same machine, being it a hydroturbine, steam, or gas. Let's see what are the main requirements for a proximity probe. Well, first of all, it must have the appropriate size and withstand the required operating conditions. That is to say, it must fit the application in its basic environmental and type of measurements requirements. It must as well show the outstanding reliability, especially important for high added value machinery, expected to work many hours without stopping. Then, of course, the proximity probe must be very precise. At the end, you need to have confidence in your proximity measurement system value. This is why there is effort and great attention in her designs to find the right balance between the three requirements and optimize the reliability to the entire chain.
there are different technologies that can be used for proximity measurements. You can have capacitive sensors, ultrasound sensors, optical, laser, and many others. Each one of these technologies has advantages and disadvantages. However, for machinery protection and monitoring, the eddy current type of sensors are the ones that offer us the best compromise between the requirements we discussed before: precision, robustness, and fit for purpose. By the way, and since I've been asked a few times, eddy is not the name of a scientist or a physicist. Eddy is the swirling of a fluid and the reversed current that is created when the fluid is in a turbulent flow regime, and this fluid dynamic phenomena is similar to the currents that are induced by a magnetic field, hence the name eddy sensors. If we want to name scientists that were fundamental to eddy probes, we must name Faraday and Lenz that define the equations we use today to design this type of probes. The eddy current proximity sensors are based on a resonance circuit formed by the extension cable and a coil in the teeth of the sensor itself. If we excite the resonance circuit formed by the cable and the coil in the sensor, this current will generate a magnetic field, a variable magnetic field in front of the sensor. Now, if we place a target, a metallic target, within the range of this magnetic field. This magnetic field will induce currents, eddy currents, in our target. And these eddy currents, by themselves, now they will also generate a magnetic field. And is the interaction between these two magnetic fields that will give us a change in the current that is generating the first magnetic field, and that we will use to generate a voltage or a current, depending on the type of conditioner we are using, that will be proportional to the distance between our target and the tip of our sensor. If we move this target, the induced currents will be higher or lower. The countermagnetic field will also be higher or lower, depending on the direction of the movement, and this will have an effect that will be measured and that will be outputted accordingly.
For this first demonstration, we will visualize the magnetic field generated by the TQ IQS chain. For that, we made a very simple sniffer with several loops of electrical wire to create a coil to capture a portion of the magnetic field. The output of this sniffer is connected to an oscilloscope. We can observe the closer we get, the more the voltage increase. The captured signal is a sinus. This sinus is generated by the IQS itself. For this second demonstration, we will see the variation of the voltage measured at the output signal when the target is moving. We can do this measurement also with the raw output. So, as we have seen in the first example, here is a representation of the magnetic field generated by the IQS. So it's a sinus wave at above 1 MHz frequency. Here is a shaker at 159 Hz. The displacement is 20 microns. So with the TQ IQS, we will be able to see the signal. But for that, I have to change the scale in order to see the signal, which is a low frequency vibration. So here is the signal of the shaker, and we can just have a quick look on the magnetic field, and we can see that it's at a higher frequency. So with the TQ, we are able to measure low frequency displacement.
The new IQS 900 has additional features that are very welcome in the field. These are a raw output, a test input, and an embedded diagnostic feature. The raw output signal allows a sensor or a measurement chain to be verified without disconnecting any outputs from the IQS 900 signal conditioner. The raw output will be always in voltage, regardless of the output of the IQS being in voltage or current. With a simple voltmeter, we can evaluate the state of the conditioner and also have an idea of its output. Note that the sensitivity of the raw output is different from the sensitivity of the conditioner for practical reasons. The test input allows us to inject an AC signal that will be added to the original signal being measured. We can observe the result of this injection either in the raw output directly, either in the TQ-IQS output or in VibroSite. Used together, the test input and the raw output allows you to test the conditioner without the need of redo or change any wiring.
Let's inject a signal on the test pin and observe how the raw output will react. If we connect now the TQ-IQS to a MPC4 MK2 slimline, for example, we can observe in VibroSite the original vibration signal at 159 Hz, and also the text signal appearing at 200 Hz.
As we have seen, the raw output and the test input are quite practical. Note that the raw output is protected against short circuits, so if by bad luck you do a short circuit on this pin, the main output will not be affected. Your measurement system will still work as expected. And this is the main advantage of having a local raw output instead of using the main output for your measurements. The raw output and the test input pins are also very convenient when used together. They will allow you to do a partial proof test with very simple equipment, locally, and without the need of changing or disconnecting any wiring. Be of course aware that the signal injected in the test pin will be added to the sensor signal and appear in the output pin. So when you use this test pin, you may need to do something in your measurement systems depending on the alarms that are defined. The third additional feature is the built-in self-diagnostic. The IQS circuitry detects open or short circuits in the sensor, open or short circuits in integral cable or extension cable, and issues in the conditioner power supply or internal components. Whenever any of these defects is detected, the output will automatically go out of scale, above or below the useful range. You can therefore define your sensor OK levels accordingly and be sure that if there is a problem with your proximity chain, you will know about it. Let's discuss now some common field issues. The first one is wiring. Good quality and cared installation are essential to have good values from your measurement system. There are different types of cables, different types of adapters that should be used, but you really must focus on having a clean installation and making sure that the cables you are using are the correct cables. Don't forget as well that, as we saw in the beginning of the presentation, the integral cable is part of the sensor, and though TQs are not sensitive to pyroelectric effects, unnecessary movements or vibration of the cable should be avoided. This is mainly to increase the reliability of the measurement system. The cable must be properly installed, well secured, and without any excessive bendings. The cable length of the sensor must also match the IQS that is being used with. Also, do not forget to follow the user manual recommendations when installing cable extensions. Now, grounding is by far the most common issue in the field. Here we talk about two different things. The first is choosing the right cables and understanding their effect on the measurement chain. I invite you to read our recent application note on this topic. It is a very complete application note, and you will see how the cables can affect your measurements and what you can do about it. The second aspect is how to connect them properly. There are some good practices that shall be followed. Let's look now with a bit more detail how to wire the proximity chains. This is the wiring diagram that you can find in the installation manual. Here we can see the sensor part, the signal conditioner part, and then here is the potential monitoring system that can include or not galvanic separation unit like the GSI 127. We have three standards that we should consider when we talk about grounding and shielding. These are the API 670 that provides us some guidance and imposes in fact some rules that we should respect, even if outside the application they should be considered as good practices. We have the exclusive environmental standards that gives us also some rules that we must follow to be compliant with those standards. And then you have the general electromagnetic compliance standards that imposes also some rules to make sure that our system is not perturbing our systems in terms of emission, but also that it is immune or not susceptible to emission from other devices. Before going to detail in the different connections, we need to separate ground from shield. Grounding and shielding are of course a common subject. We cannot talk one without talking about the other. but we must bear in mind that they have two different purposes. Ground or grounding is normally something functional. It's used to protect us, so he has a safety um, function to protect us against electrical shock, and has also another function which is related to our signals. Ground is to provide us a common reference to all our signals, and ground normally is very important, especially in low and mid frequencies. Shielding is non-functional. Shielding is to increase the immunity of our system to external electromagnetic fields, and also to reduce emission of our system to not perturb the other ones. So shielding, we should think about it more something like important at mid and very high frequencies, while ground we should be concerned and should focus more on low and mid frequencies. And this difference will explain some choices or some decisions we made to define the wiring of the proximity system. Let's start by the proximity probe. The proximity probe is floating, so the electronics of the proximity probe are not connected to the ground. The casing is connected to the ground, so if we take a proximity probe, the thread, the metallic part will be connected to the ground of the machine. However, it's not connected to the ground of the cable. So the probe is considered floating. If you have a metallic protection sleeve for explosive environments, you are obliged to ground it. And you should do this with dedicated ground connection. It's not recommended to rely on the ground connection provided by the thread. You should have a dedicated ground connection to it, because the thread is not made to give a electrical contact. It's designed for mechanical purpose but not for electrical purpose. So for ATEX standards, it's recommended to use ground connection in the metallic protection sleeve, and this is because the EX standards, they require that every metallic part must be connected to the ground to properly dissipate any electrostatic charges. Okay, so the sensor will be considered floating. Now the conditioner, it should also be considered floating. One of the reasons, more related with historical reasons, is that the fact that it is provided, that is supplied with minus 24 volts. There are cases when you have a 24 volts power supply, but where the negative of this power supply is connected to the ground. So if you try to connect that negative to minus 24 volts and the positive to COM to obtain the minus 24 volts, you have a short circuit that will not work. It's one of the historical reasons that's pushed most of the proximity probes to be considered floating to avoid that problem. So these units are floating locally. We have the option of a DIN adapter that is isolated from the casing. This casing is connected to the COM and also to the shield of the probe. But with this plastic DIN rail adapter, it will be isolated from the DIN rail. So this part should be floating, and you simply connect the sensor to it without any other connection to the ground. Leaving the conditioner, if we have a two-wire transmission cable, you will have the minus 24 volts connected to the sensor power supply of the VMC standard or the MS, or to the negative of another power supply, API power supply, for instance. And the COM, so it's a current mode transmission. You have two-wire transmission cable. So this COM should be connected to the input of our monitoring and protection system, to the IQ input, and should be done by the internal cable in your K2 cable. The other connection, called also COM, should then be connected to the shield of your cable, and this cable at the entrance of the cubicle should then be connected to the ground. And here is we have two very important things to consider. First, on the conditioner side, this connection, especially to the shielding of the cable, should be properly done, and this wire here should be as short as possible. And then the entrance of the cubicle is also very important, that the cable, so you have outer shielding of the cable, and this should be connected with a proper clamp to the ground. And this is to ensure that you minimize the impedance of this cable for mid and high frequencies, because this cable in the middle part of your transmission system will give you the reference to your system. So you will be concerned a lot more with low and mid frequencies. However, the shield that will protect you from electromagnetic fields from the external, and also avoid you to radiate to the outside, is much more important for high frequencies. And if you don't have a very solid connection around it, you will have higher impedance at lower frequencies, and the shielding will not be as effective. Of course, the same applies if you have a three-wire transmission cable, if you are in a voltage mode. Again, you have the minus 24 volts, the COM connected now to the low of your system, and the output will be connected to the high. And these three signals will be like these two, carrying your information, your electrical signal that will send the sensor information to your system. We have also, like in the current mode, another connection to a COM that should be connected to the shield, again with the same consideration that we did before. So you can consider this as shielding, as it is often said, shielding on one side only, because this part will be connected to the ground and entrance of the cubicle, and this part outside will be considered floating locally. Of course, the shield here, and the COM and the shield here will be all at the same potential, but they will be considered floating locally and only connected to the ground at the entrance of the cabinet. And this is, by the way, a very good practice and a general rule. The best point to protect your system from non-compliance in terms of electromagnetic radiation conducted as well, is to have a solid ground connection in the entrance of your cubicle. The reason is that the cables in this region, they will be very long. They can be very, very long, especially between the conditioner and the cubicle. So you have big antennas. You will be collecting a lot of electromagnetic energy that you don't want, and that entrance is the best way to dissipate these energies, so that they don't affect all the instrumentation that is inside your cubicle. If you have two cubicles, you should apply the same rule. So at the entrance of each cubicle, and also in the exit of each cubicle, you should have a good solid connection. As a summary, consider it shielded only on one side. Be very careful with this connection to the ground and with this connection to the shield. Sorry, here is to the shield as well. They should be very well connected, short cables, proper cables, And if you have housing, to make sure that all your string leaf protections are designed according to not cause excessive deformation of the cable. This part again floating, and this part connected to the ground. Let's look now into some practical aspects related with the probe mounting. As we saw, the measure of the distance depends on magnetic field generated by the sensor and by the currents in the target, so there are several aspects related to the mounting of the target that should be considered. The first one is the gapping of the sensor. The initial distance, or the middle point of your measurement, should match the middle point of the range of the sensor, unless of course you expect an asymmetric movement. You can then compensate this value in vibrosight. It is very important that the sensor always works in its linear region. Another important aspect is to have a minimum free area around the sensor. This is to avoid any distortion in the magnetic field generated by the sensor tip. If it is too close to other metallic parts, the magnetic circuit will be influenced and the output will eventually be nonlinear. It is also important that there are no other sensors below the recommended distances. Not only the magnetic fields of each sensor would interfere between them, but also the magnetic field generated by the eddy currents in the target would also interfere between them. These distances are mentioned in the installation manual. For rotors, there is also a minimum diameter that must be respected, otherwise the measurement will have an error. If two sensors are used, then you will have crosstalk and you will end up with additional noise in the output if the diameter is below a certain value. You can find this information also in the installation manual. An often neglected part is the mounting plate. If the mounting plate is not solid enough, it will also vibrate and falsify your measurements. For the mounting plates and also for the sensor itself, you need to apply the correct torques. Of course, an excessive torque in the sensor can damage it, but if the torque is not high enough, it can vibrate. All this will affect your measurement at the end. There are different mounting options and TQ models for different applications, and again you can find all these details, including for instance the required torques, in the TQ IQS installation manual. Finally, the target material will also influence the measurement. It is important to know what type of target material will use with your sensor. By default, Megit's TQ IQS proximity systems are calibrated for VCL 140 alloy steel. This is a very common high-quality alloy that is used typically in construction of rotors. If you have any other type of metal or alloy, you can compensate the value in vibrosight so that you can use your TQ and still have linear output. The new IQS 910 that will be launched in the beginning of 2023 responds to a market demand for a conditioner with a standard 420 mA output and also for an easy and seamless peak meter for vibration measurement. With a standby current of only 4 mA, the conditioners can be very easily integrated into a current loop. The IQS 910 will be available in two versions. One like the current IQS 900 but with a more generic 420 mA output, and the second version will have an integrated vibration peak meter processing for vibration measurement. This version will therefore provide a slowly varying DC signal that responds to the peak values of the vibration signal. These versions will have similar certifications like the QS 900, including SEAL, and keep as well the raw output, test input and self-diagnostic capabilities.
Here is the IQS 910. So the IQS 910 is power rate between 0 and minus 24 volts. But as it's a current output, we put in place a resistor in order to have a voltage visualization of the signal. So here we can see the signal, which is a little bit above 0, which is in fact the representation of the standby current, which is roughly above 4 milliamps. Now, if I use the target, a vibration target, and we see here an overshoot, the rising time of this overshoot is roughly 70 milliseconds. And then the signal will stabilize to a level which is a representation of the standby current and the peak of the vibration current. So the overshoot 70 milliseconds, fall down roughly more than 4 seconds, and stabilized to a value which represents the sum of the standby current and the sum of the peak of the vibration. So the IQS 910, as the other IQS, has the raw data. So here is, with a multimeter, we can measure the voltage at the raw output. So here we can measure minus 9 volt, and if we have a vibrating target, we can see the raw value going up to minus 6 volt. So thank you for watching this webinar, and now we will take your questions.